So, good evening, guys. I welcome you all to a new session on solving previous year questions which are asked in GATE Aerospace in the area of flight and space mechanics. Okay. So, my name is Praveen, and today we'll be focusing on the questions which are asked in the year GATE 2014. And so, in this year, particular year, they ask four one-mark questions and five two-mark questions. So, this is only an exception, no? Where which they ask questions below 16 marks. Okay, but nonetheless, let's do this. So before going into the 2014 questions, so the previous session, we were solving questions, right? One, two questions I was not able to solve it, and I told that I will be uploading the solutions, right? So let's do that now, and then we'll jump back into 2014, right? Okay. So let's get started. So this was the question which we did in the last class. So let's redo this again. My answers were wrong, okay, because I didn't have that much exposure to aerodynamics, and it's been 3 years since I touched that, right? So let's take this question. So circulation theory of lift is assumed for a thin symmetric airfoil at an angle of attack alpha, and wherein the free stream velocity is u. If the circulation of the quarter chord of the airfoil is gamma 1, the normal velocity is 0 at dash. Okay. So let's try to do this pretty simple one. Okay. So let's consider an airfoil, simple airfoil like this. So there is a circulation in here, capital gamma 1 like this. So it is at this distance of c by 4 in here. Let's say this distance is, let's mark a point in here, at which let this be point q. Let this be a distance y. So point q, at point q, your normal velocity is 0. Okay. So this is what you have to remember, right? The normal velocity is 0. You have to determine the point. Okay. So let's say that free stream is coming in at an angle of attack of alpha. So for determine the velocity at point q. So if you see the point q in here, I have velocity coming from this circulation which is in downward fashion, and you can get it as gamma 1 by 2 pi times y minus c by 4, correct? And I have also an upward velocity which is basically my u. Let's say this is u infinity, and this will be u infinity sine alpha, right? So which means if I simplify this, then what will I get is, so u infinity sine alpha minus gamma 1 by 2 pi times y minus c by 4. This is equal to 0, correct? Yes. So which means that, if I simplify this a bit further, let's invoke the small angle approximation, invoking the small angle approximation. What do we get? So we'll have u infinity alpha is equal to gamma 1 by 2 pi times y minus c by 4. Okay. Let's bracket this and keep it aside. Okay. Mark this as equation number 1. From our thin airfoil theory, you can write it over here. From thin airfoil theory, what is my CL? It is 2 pi alpha, right? Therefore, what is my lift? We know the formula for lift is half rho v square. S in this case is C and times CL, which is basically I can write this as half rho u infinity square C times 2 pi alpha, right? But this lift is also equal to my Kutta-Joukowski theorem, which is rho capital gamma u infinity. You can equate that half rho u infinity square C times 2 pi alpha. So which means if I simplify this, I can get the expression for u infinity alpha as what? Capital gamma by pi times from this. Okay, cancelling out the left and right and common terms, we'll get like this. So if I substitute it back into in here, so my y would become simply this again gamma 1, mind you. So substituting this in here, so substitute, then my y would become 3c by 4. Okay, so that is my answer. Bracket this, guys. Okay, so if we go back to the options, the correct option is option C. Okay, 3c by 4. Hope you guys understood this, right? So this is the first part. Okay, so now let's dwell on into the second part. This is the second question. A second identical airfoil is placed behind the first one at a distance of c by 2 from the trailing edge of the first. The second airfoil has an unknown circulation gamma 2 placed at its quarter chord. The normal velocity becomes 0 at the same chordwise location of the respective airfoils as in the previous question. The values of gamma 1 and gamma 2 respectively. So we have four options: 4 by 3 pi c u alpha, 2 by 3 pi c u alpha, then we have 2 by 3 pi c u alpha, and 2 by 3 pi cu alpha, and we have the other two options. Okay, so let's try to do this again. Simple problem. So I have this airfoil like this. He says there is another airfoil, identical airfoil, which is kept at a distance of c by 2 from the trailing edge of the first airfoil. So there are two circulations in here, capital gamma 1 and capital gamma 2. So again, these are kept at a distance of c by 4. This also kept at a distance c by 4. And here my normal velocity is 0, right? So which means this distance is, because this is 3c by 4, this distance has to be c by 2, correct? Right. So let's take this point, sum of the velocity, sum of the velocity at point q, wherein at the point q, the normal velocity is 0 as determined, right? So which means I can write again, do the same analysis. This is u infinity at an angle of attack alpha. So I will get what? I have u infinity sine alpha. Let's do the small angle approximation, then you will get it as u infinity alpha. So let me write that down as well. Then because of this q, so if you have q, you see gamma 1 is causing the velocity is in the downward direction, minus capital gamma 1 by 2 pi times c by 2. And if you look at gamma 2, for gamma 2, the component of velocity is upwards in q on q1, right? So which means you will have plus gamma 2 by 2 pi. So what will be the distance? C by 4 plus c by 2 plus this c by 4, right? So you will have 1 c. Okay, this is equal to 0, right? So if you simplify this, you will get an equation as minus 2 gamma 1 plus gamma 2 is equal to minus 2u alpha pi c. Bracket this. Okay, this is the first thing. Next is, now we know the Kuta-Joukowski, right? So from the KJTZ theorem, Kuta-Joukowski theorem. So I can write the total lift as rho u times gamma 1 plus gamma 2 would be equal to half rho u square. Here in this case, because we are combining the both the chords, so this will be 2c times the CL is 2 pi alpha, right? This is basically CL and half rho u square, right? So if I simplify this again, so you will get capital gamma 1 plus capital gamma 2 would be equal to 2 pi cu alpha. Okay, bracket this. So again, simplify this, solve. We have two equations and two unknowns. If you solve this, so I would get gamma 1 and gamma 2. Let's mark this as equation number 1, mark this as equation number 2. Solving 1 and 2 to get the unknowns, which are gamma 1 and gamma 2. So we have what? Gamma 1 is simply 4 by 3 pi c u alpha. Gamma 2 is 2 by 3 pi c u alpha. Okay, so these are the two values of the circulation. And that is my option. Yes, guys, hope you guys understood this. Again, I'm sorry for not doing this problem in the last class, right? Okay. So with that behind, so let's start with the 2014 questions. Okay. So let's take the first problem. So the moment coefficient measured about the center of gravity and about the aerodynamic center of a given wing body configuration is 0.0065 and minus 0.0235 respectively. Full stop. The aerodynamic center lies 0.06 chord lengths ahead of the center of gravity. The lift coefficient for this wing body is a pretty simple problem. Okay, so let's do this. So we know the equation, right? So we know that CMCG is equal to CMAC plus CL times XCG bar minus XAC. Okay. So he says that aerodynamic center, let's mark the distance. Let's say this is the leading edge. From here, we're measuring distance. Aerodynamic center lies 0.6 chord or ahead of this CG, right? So which means aerodynamic center is ahead. So this is my AC and this is my CG. Okay. So this is my distance is 0.06. So you know this. This is 0.06. He's saying that this value is 0.0065, and about the atomic center for a given body, this is basically minus 0.0235 plus CL times 0.06. Simplify this, you will get the CL obviously. So CL will closely come around to 0.51, I think. Okay, just do this very simple. Okay? Right? So this is my answer. Okay, guys, I hope you don't have any doubts in this, right? So if not, then we go ahead. Take this next question. The vertical ground load factor on a stationary aircraft parked in its hangar is dash. So we have four options: 0, -1, not defined, and 1. Okay. So from theory, we know that N is equal to L by W, right? So if I try to use that, then that becomes, you will say there's no lift for stationary, hence N is 0. But that's not the case, right? Because when you have an aircraft parked, basically, the reaction, basically the ground offers reaction, right? The reaction balances the weight, right? So you have to pre-modify your definition accordingly, right? So for this case, for a park, stay a vertical load factor on a stationary aircraft, okay, park. This can be written as W minus L by W, okay. It's basically the reaction effect, okay. This is basically the reaction force, right? So for stationary aircraft, we know that lift is equal to 0, so hence what? N is equal to 1. Okay, so this is the thing. So you can just write down, can just write a note in here, right? So the load factor is the ratio of load factor N, okay? The total aerodynamic force acting on an aircraft to the weight of the aircraft. However, for an aircraft is parked and isn't moving, no aerodynamic force acts. No aerodynamic force acts. Okay, so this is the thing. So I have to remember this, right? Okay. So if no doubts, then let me go to the next question. Right. So take this one. Under what conditions should a glider be operated to ensure minimum sink rate? Okay. So sink rate, underline this one, minimum sink rate. So sink rate is basically, it's another term, so it's basically the rate of descent. Okay. Rate of descent is basically an unpowered flight. Okay. So basically how fast the aircraft is going down. Okay. That's it. This is the net speed with which the aircraft is going. This is the vertical velocity. This is the horizontal velocity. Okay. This is u. Okay. This is velocity vector. Okay. So this is the sink rate basically, right? Which is the rate of descent, and this occurs at the minimum power condition. Okay. So at the minimum power condition. So minimum power means what? So minimum power means your C by CL power 3 by 2 should be minimum. Okay. This should be minimum. So which means that my option is D. Okay. So for more details, you can just refer to aircraft performance by Anderson. Okay. It's given detail in detail. Okay. Okay. So if no doubts, then again let me go ahead. Right. This is pretty simple. That's all you have to do is just revise the formulas. Mostly from the formulas, they will ask you to test. They'll test on your understanding ability. Okay. So you have to use formulas and then try to make sense of the results. Okay. Right. So let's go to the next question. In most airplanes, the touch roll can be excited by applying. So we have four options: a step input to the elevators, a step input to the rudder, a sinusoidal input to the aileron, an impulse input to the elevator. Okay. So first, we have to understand the Dutch roll. Okay. So what is a Dutch roll? So Dutch roll happens, when there is a strong lateral stability, but there is a weak directional stability. Right? So it means it can ease a weak direction. So when there is a weak disturbance, it gets affected. So it means if you give a disturbance to the rudder, the Dutch roll is excited. So hence, the answer is option B here. So while giving a step input to the rudder, you basically, ensure that you enter Dutch roll mode. So basically, Dutch roll is like this. Imagine. Let me just give an example. Let's say that you have a ball like this. Okay, you push it. So what will happen? The ball will follow a straight line. It will reach here, right? So suppose let's consider another ball which you're starting it here and you're pushing it in this direction. So basically, what happens? The ball will reach here. After some time, it will come here. After some time, it will come here. At some time, it will come here, and so on. Right? So basically, this is basically a Dutch roll. Okay, hope you don't understand this, right? Yes. Okay. So just remember this. Dutch roll. Okay. So that happens when you have a strong lateral stability but a weak directional stability, right? Okay. So if not else, then let me go ahead. For a given airplane with a given wing loading, executing a turn in the vertical plane, under what conditions will the turn radius be minimum and the turn rate be maximum? So we have four options: highest CL and lowest N, lowest CL and lowest N, lowest CL and highest N, highest CL and highest N. So it's saying executing a turn in a vertical plane, okay? And turn radius is minimum and the turn rate is maximum. So the vertical plane is basically, in this plane. You're analyzing in this, so which means your maneuvers basically, the pull down or the pull up maneuver, right? Pull. So which means now let's take the pull down maneuver. So you know that the formula is basically what the radius of curvature is basically turn radius is v squared by g times n plus one, and the omega is basically uh, g into n plus one by v. Right? So these are the two cases. So which means, and also just put in v as what 2w by rho SCL whole under the root, right? So this is expression for the V. Right? So it's saying, given R is minimum, omega is maximum, right? So R minimum happens when we just discussed in the last session. It happens at V minimum and N max, right? And this also happens at, N max. This has to be a max. So this is max and this is min. And when does min occur? So V min occurs when the CL is maximum, right? We're just manipulating, right? So which means what? For R min to occur, we need to have a V minimum, which implies a CL max, right? At the same time, we need to have an N max. And same goes for this thing, okay? Omega max, okay? So hence we need both, just write it. We need both N max, which is the highest possible load factor, and the highest possible lift coefficient, CL max. So going down the option, so this is the only one which has our answer, right? Hope you guys understood this, right? Any doubts in here? No, right? Okay, fine. So if not, let me go ahead to the next question. Liftoff distance for a given aircraft of weight W is SLO. If the takeoff weight is reduced by 10%, then the magnitude of percentage change in the liftoff distance is dash, assuming all the parameters to remain constant. Right? So what is expression for the liftoff distance? Pretty simple again. So liftoff distance is SLO is 1.44 W takeoff weight square by rho GSCL times your thrust minus drag minus mu times the difference between the weight and the lift, right? So he's saying that if the takeoff weight is reduced by 10%, right? So that is if WTO is reduced by 10%. Then my new WTO prime would become what? 0.9 times WTO, right? So, which means that from the above equation, I can say that SLO is proportional to W square. Bracket this, okay? Let's come back here, right? So, which means that if I determine the change, percentage change in SLO, which is delta SLO, that is basically my W takeoff with prime minus W takeoff by W takeoff. So if you simplify that, you will get a value of around 19%. Okay, so this is the decrease, right? So you guys understood this. So it's only asking the percentage, so just write it as a positive value. Okay, 19%. Right. You don't have to worry about the plus and minus because it's asking the magnitude. Okay. If you ask the percentage change means you have to give a negative, say minus 19. Okay, there is a 19% decrease, right? But if they ask specifically the magnitude, then you have to give in the value. Don't give a minus, or else you will lose silly mark. You are making a silly mistake there, which implies you lose marks. Okay, so please be careful. Read the words clearly. Okay, right? So then let's go to the next question. Which of the following design parameters influence the maximum rate of climb for a jet-propelled airplane? So we have four options: wing loading, maximum thrust to weight ratio, zero lift drag coefficient, and maximum lift to drag ratio. Right? So maximum rate of climb, underline this thing, of a jet-propelled airplane. So what is the expression for the maximum rate of climb? So must write down the rate of climb expression. So it is basically T minus d by W times the velocity, right? So which is basically my T minus d by W times under root of 2W by rho s CL, right? So let's take the CL inside. So which means you will have what? T by W times CL power minus half minus d by W times CL power minus half times under root of 2W by rho s, right? So simplify this. So you'll have T by W times CL power minus half minus d by W. You can just write the d by W as simply, it is CD naught plus KCL square, right? So which means I'll have CD naught plus K times CL square and times, and simplifying this, you'll get around a CL power minus 1 again. So you'll have a CL power minus 1 by 2, so which is minus 3 by 2. And when this math are pretty simple, okay, you can just do it, okay. So this will be under root 2W by rho s, right? So which means if I compare the expressions, he says, it depends on wing loading. Does it depend on wing loading? Wing loading is W by S. Okay, so let me write down that. So the wing loading is W by S. What else is given? It depends, right? Let me use different color so that you understand that. This is the term. He's saying maximum thrust to weight ratio. Okay, this is the term. Okay, thrust to weight ratio. Let me just write that down as well. Or else let me mark it and then let me write that. Okay. And what else is given? Zero lift drag coefficient, which is CD not in here. Okay. And what else is given? Maximum lift to drag ratio, which is also in here, CL. Okay. Which means let me write that down one by one. So it's saying maximum thrust to weight ratio. So let me write down thrust to weight ratio. This T by W. Lift to drag ratio is CL by CD, and no zero lift drag coefficient is CD not. Okay. So which means it depends on all of the parameters, right? The answer has to be option B. Yes, pretty simple, isn't it? Like I said, it is very easy. If you start doing problems like this, you will end up solving them in a matter of seconds. Okay, provided you understand the concept behind and the know-how of applying formulas in it, right? So we still have two more questions, and let's do that. Consider the following four statements regarding aircraft longitudinal stability. So CMCG at zero left must be positive. Let's mark the statements first. It's not given, so let this be statement number P. statement number Q, statement number R, statement number S. CMCZ zero lift must be positive. Dou Cm by dou alpha must be negative, where alpha is the absolute angle of attack. CMCZ zero lift must be negative. Slope of Cl versus alpha must be negative. Which of the following combinations is the necessary criteria for a stick fixed longitudinal balance and static stability? Okay. Let's analyze these statements. Okay. He's saying slope of Cl versus alpha must be negative. So we know that from our thin airfoil theory, Cl is linearly varying with alpha, right? For symmetric case. Okay, let's take that. And let's forget the stall regime for now. Okay. If the slope is negative, what do you think will happen? Just like this basically, which is not practical. As angle of attack, this CL decrease, which is not all good way to control an aircraft. Right? So this can't be the case. Okay. Like CMCJ zero lift must be negative, right? So let's look at that from the stability theory. If we rewind back from the stability theory or the stability analysis. So these are the conditions. CMCG must be greater than 0, and your CM alpha, which is basically dou Cm by dou alpha, must be less than 0. So this is the graph, and this is the intercept, which is Cm naught, and this is a plot of Cm versus alpha. Okay. So this ensures longitudinal stability. Okay. This ensures longitudinal stability. Right. So this means if I go back to my options, so this is a correct thing. Cm should be positive and it must be negative. So the answer, only option is P and Q. Okay. Hope that makes sense, right? Hope you don't have any doubts in this case, right? Yes, pretty simple. Okay, like I said, from stability questions that are asked are very simple, but they are big in nature, monstrous in nature, because they are the question the people who set the paper, they wanted to confuse it. They make a mockery out of it. Right? So don't have to then get afraid upon seeing these questions. When there is a big question, it means that you can easily arrive at an answer within a step. Okay, that's what the logic is about. Okay, right. Let's look at the last question of today's session. Take this question. Data for a light, single engine, propeller driven aircraft in steady level flight at sea level is as follows. V infinity is 40 meter per second, weight is 13 kilonewton, lift coefficient is 0.65, drag coefficient is 0.025 plus 0.04 CL square, and power available is 100 kilojoules per second. The rate of climb possible for this aircraft under the given conditions is dash. Okay. We have four options: 7.2, 5.11, 6.3 to 4.23. Pretty simple. Let's do that. So we know that the rate of climb, is nothing but the excess power by the weight, right? Which is what I wrote over here. Which is basically my thrust minus drag times the velocity by W, which can be written as the power available minus power required divided by the weight. Okay. So let's write on the given info. So the power available is given as what? It is 100 kilojoules. So joules per second. Next, weight is given as what? 13 kilonewton. And the free stream velocity is given as 40 meter per second. And CL is given as 0.65. So therefore, from that drag polar determine the CD. Okay. So CD equal to 0.025 plus 0.04 CL square. Substitute it over here to get CD, right? So which means how can I determine the power required? That is the only unknown. Power required is basically your thrust required times the velocity. What is thrust required from the formula? It is basically W by CL by CD times the velocity. Right. So we simplify this, substitute all the values. You know CL and you get CD from this expression. You know the weight, you know the velocity. So if we do that, so we get the value of 33,520 joules per second. So therefore, what is my rate of climb? It is basically again substitute the value, power available minus power required divided by the weight, which is 13 kilonewton. So we'll get a value close to 5.11 meter per second. So that goes to option B, which is the required answer. Right? Pretty simple, isn't it, guys? Okay. So with that, we are at the end of today's session. I hope you guys have understood something out of this session. And please solve previous questions again, because we only have about a week or so. For the D-Day, which is your gate exam, aerospace engineering examination. I want all of you guys to do well, right? So please practice these problems. That they will basically repeat problems on the lines of these concepts that we applied, so far, right? So please subscribe to the IGC channel, and I would like you to thank. I would like you guys to please keep watching our videos, and please motivate us so that we'll make videos like this more in the future, right? So thank you guys, and have a good day. See you. Bye bye.